This second experiment that's focusing on acid-base chemistry is a little bit more in-depth than the first one that you did for the last experiment. In the last experiment, you were looking at the overall chemical reaction of an acid and a base. The H+ acid ion reacting with the OH- base ion to form water. This experiment looks at measuring the pH and converting that into a concentration of H+ and a concentration of base for varying solutions. It also looks at the equilibrium reaction of these acid-base reactions. You've already looked at equilibrium reactions in other types of chemistry and other types of reactions, and this focuses on the equilibrium between those acid and base ions as they react with each other. That interaction and that equilibrium between acid and base plays a critical role in the formation of buffers. And buffers are something that is a mixture or a blend of an acid and a base that are in equilibrium with each other, where they maintain a constant or relatively constant pH. Because of the chemistry and because of the equilibrium between the acid and the base, a buffer solution is resistant to changes in that pH. If you were to add a little bit of acid or a little bit of base, the pH itself maintains a relatively constant concentration or relatively constant value because of the equilibrium chemistry. So in this experiment, we're looking at measuring the pH of various different solutions, as well as preparing buffers and determining through experiments which buffer is better for these varying types of situations. Which one has a better buffering capacity for an acid, and which one has a better buffering capacity for a base. This experiment is the second acid-base experiment that you're performing in the class. Where the first one was more simplistic and just looking at the reaction of acids and bases, this one looks more at the equilibrium between those two and the equilibrium of acid-base reactions, as well as the concept of buffers and buffering capacity. In the virtual lab, you're going to be preparing two different buffer solutions. You're preparing an acetate buffer, which is acidic and will have an acidic pH, and an ammonia buffer, which is a basic buffer, would have a basic pH. That's the first step in the lab, is just preparing these buffers. Once you have the buffers created, you're then going to see how they interact with acid and how they interact with base. So you're going to take both of those buffers and to each of them add a little acid and see how they react, and then add a little base and see how they react. And you're going to be using the pH of both your buffer, the stock solutions, as well as after you react the buffers with either acids or bases, looking at the pH of these and using those to determine which one has a better buffering capacity and for what type of compounds. So as mentioned in the previous lecture, you're looking at the pH scale, and pH is a measurement of the concentration of H+, or the concentration of acid. So the pH is the negative log of the concentration of H+, typically ranging from 0 to 14. And it's a log-based scale. And you can use this to convert between pH and concentration of acid, or concentration of H+. The pH value can also give you more than just that. The pH value can also give you the concentration of base. Because the pH ranges from 0 to 14 based on the equilibrium dissociation constant of water, Kw, from the pH, you can also determine the pOH. And the pOH is the negative log of the concentration of OH minus, or the concentration of hydroxide, base. And when you add the pH plus the pOH, that gives you 14. Again, this is based on the dissociation equilibrium constant of water, that 14. So if you have the pH, you have the pOH, and from the pH, you can determine the concentration of acid, and from the pOH, you can determine the concentration of base. So there are different ways to measure the pH of a solution. There are both chemical ways to measure the pH, and there are electronic ways. General way of measuring pH would be through the use of a pH indicator or pH paper. And these are chemical indicators that will change color depending on their environment. So in this example here, this is the indicator phenylphthalein. And at a low pH, which is an acidic solution, this is the structure. And there is no color associated with it. It's a colorless solution. However, if the pH increases and the solution becomes basic, that equilibrium change between H plus and the indicator itself causes this reaction. So the equilibrium would be this version in equilibrium with this version, the pink version, plus H plus. So in this other version of phenylphthalein, the structure has changed, and now this alternating structure called conjugation, where you have a double bond, then a single bond, then a double bond, then a single bond, double, single, double, single, double, single, all the way through. That conjugation gives rise to a color. And in this case, phenylphthalein is a bright pink or fuchsia color in high pH. So it's an indicator for basic solutions. There are a number of different indicator compounds that change color depending on what the pH is. Each of them will change color at approximately a different concentration, and some of them can change into more than one color. pH paper, which you've probably used if you're measuring the pH of a pool or something, measuring the pH of water, is another chemical indicator. And all that is the pH indicator that's absorbed onto a piece of paper. So that way, if you were to dip the piece of paper into water, so in a backyard pool, the color would change depending on what the pH is. These types of chemical indicators can give you a good general sense of what the pH of a solution is, but not an incredibly detailed concentration. For a much more accurate and much more specific concentration of pH or a concentration of acid, you would use a pH meter. And a pH meter is something stylized like this, where you have a glass tube with a little glass bulb on the end. And the inside of the tube is hollow. Inside, there's a solution with a known concentration of ions and a known concentration of H+. So that doesn't change. And you put that into the solution that you're trying to measure. And what happens is the H+ ions will kind of stick to the glass. And the H+ ions on the inside are also sticking to the glass, but on the inside. Because acid ions, H+, have a charge, there is some electrochemistry, an electrical signal being generated from this type of a setup. You have one charge on the outside, depending on the concentration, and you have a different charge on the inside. And the difference between these charges from the outside and the inside will cause a voltage. It will cause an electrical voltage that can be measured, and therefore the electronics in a pH meter can convert that electrical impulse into what is the pH of the solution based on really the number or the concentration of H+ ions that are sticking to that surface. If you move on to more advanced chemistry, you will use these types of electrodes in other areas as well. They also make electrodes like this, not only to measure pH, but other ions as well. So chloride, hydroxide, different ions can be measured with different types of electrodes. But it's a way to very accurately measure the concentration of acid ions in a solution and accurately measure the pH. The pH of a solution can be measured by 3 different methods, either pH indicator, pH paper, or by a pH meter. The solution in the beaker is a solution of sodium hydroxide. This particular pH indicator of phenolphthalein is colorless in acidic solutions and a bright pink in basic solutions. Based on the color change, this indicator can tell that the solution in the beaker is a base. However, it does not give a specific pH number to determine concentration. pH paper is a set of different pH indicators that are absorbed on paper. Similar to how you would check the pH in your home pool, a pH indicator strip is placed in the solution and then compared to the color chart to determine the pH value. By knowing the solution is basic, we can focus on only the basic half of the pH table. By comparing the different colors on the pH paper, we can determine that this pH paper indicates the pH of the solution is 12. This is the closest matched color for all 4 different pads on the pH paper. While the pH indicator solution can determine that the solution in the beaker is a base, and the pH paper can indicate that the solution has a pH of 12, the pH meter can give a much more accurate measurement of the pH. pH meters take a few seconds or so to stabilize in the solution, but you can already see that this solution is having a pH of 12.67 or 12.68, a much more accurate reading of pH than just the whole number of 12 that was given by the pH paper. Overall, the pH meter is a much more accurate way to measure the pH of a solution out to a higher level of significance to a better precision. In this experiment, you can also look at something called the percent ionization. And you've seen this before. Different compounds, different salts will break apart into their ions. But at some point, it's no longer soluble. It won't break apart anymore. So at specific concentrations, it's not going to dissociate. And what the term percent ionization means is how much of that compound will break apart into ions. And in terms of acid and bases, the percent ionization is what dictates whether something is a strong acid or base or a weak acid or base. And that does not mean its strength as far as able to undergo different reactions, but the terms strong and weak acids and bases refer specifically to the percent ionization, or how much of it breaks apart into its ions. So hydrochloric acid is a strong acid. If you have a 1 molar solution of hydrochloric acid, it fully breaks apart into its separate ions. That means there will be 1 molar H plus and 1 molar Cl minus. Sodium hydroxide is a strong base. And again, it breaks apart completely into its separate ions. If you have 1 molar sodium hydroxide, that means you have a solution of 1 molar sodium ions and 1 molar hydroxide ions. These are a strong acid and base. However, there are also the terms for weak acids and bases, and these are something that are things that do not break apart 100%. So in the case of acetic acid, this is what you'll be using to prepare one of your buffers. Acetic acid is vinegar. Now, acetic acid, pure acetic acid, is a liquid, and it will dissolve, or not dissolve, but it will disperse throughout water, but only some of it will break apart into its individual ions, some percentage. The rest of it will remain as a whole soluble molecule of acetic acid. So while a strong acid or a strong base, the solution contains only the ions, in a weak acid, the solution will contain both the ions and the pure compound itself. And when you measure the pH of something, if you know the concentration of ahead of time, you can obtain the concentration of H+, so that's the concentration of ion, and determine a percentage. So if the concentration of acid is 1 molar, and the pH tells you the concentration of H+ is 0.1 molar, that means 10% of it broke apart into its ions. The 0.1 concentration of H+ divided by the total concentration that you start it with of 1 molar. So this is something that you can also look at by measuring the pH. You can determine if something's a strong acid or strong base, weak acid, weak base, by looking at the concentration and looking at the concentration of this individual H+ ion. The differences between a strong and a weak acid can be seen through the percent ionization of hydrochloric acid and acetic acid. Both the hydrochloric acid and the acetic acid are at concentrations of exactly 0.100 molar. With the accurate pH meter, when the pH of the hydrochloric acid solution is measured, the pH is near to 1 pH units, or 1.01 pH, or even exactly 1. However, when the pH meter is placed in the acetic acid at the same overall concentration of 0.100, the resulting pH is now over 2. This is because acetic acid does not fully ionize. Therefore, there will be less of a concentration of H+ than the original solution. Based on the measurement of pH, you can determine the exact concentration of acid present in the acetic acid sample. And then dividing that by 0.100, you can obtain the percent ionization that occurs for acetic acid. Now, a strong acid or a strong base is pretty straightforward. It breaks apart, it goes from the acid molecule into its ions, and that's it. It's 100%. But weak acids and weak bases that only break apart to a certain percentage have a little bit more detailed chemistry, because in these situations, it's an equilibrium. There is an equilibrium between the whole acid molecule and its broken apart ions, the H+ and the counter ion, the conjugate base ion here. So in the case of acetic acid, you have acetic acid breaking apart into H+ and the acetate ion. In the case of a weak base, ammonia reacts with water to generate ammonium and hydroxide. And not all of the ammonia will react with the water to form these ions, only some of it. It's an equilibrium between how much they dissociate. And the equilibrium constant for these equations is termed the Ka for an acid dissociation, or a Kb for a base dissociation. These are just like the equilibrium constants of the previous, kind of in the previous section where you had Keq. It's the same exact setup, it's the same exact calculation for determining these K values. The A and B just indicate that this is for an acid and this is for a base. These subscripts on an equilibrium constant only mean the type of equilibrium that it is, but the calculation is still the same throughout it. There are also other types of acids, particularly weak acids, that are polyprotic. That means they have more than one proton or more than one acid, H+. And in the case of phosphoric acid, there are 3. The phosphoric acid molecule is H3PO4, and it's a weak acid. That means it does not break apart all the way. And each one of these H+ ions breaks off one by one. So in the case of phosphoric acid, there are 3 separate equilibrium constants to dictate each one of these 3 separate reactions.
So when you're trying to determine the Ka, or the equilibrium acid dissociation constant from a sample, you need two values. You need to know what is the starting concentration and what is the pH. The pH value is a direct measurement, and this value is measuring the solution or the system at equilibrium. And typically when you're preparing these solutions in a lab setting, you're preparing a solution or a sample of something, you're weighing out or you're measuring the amount of pure acetic acid, not its equilibrium amount. So this would be initial. So going through these types of ice tables, you're looking at if time was frozen. If you mixed all these together at time equals 0, initially in this example, a 0.10 molar acetic acid sample has a pH of 2.88. What is the Ka? So initially, there is 0.10 molar of acetic acid. And before it breaks apart, before time starts, you have a concentration of H+ and acetate ions of 0. However, this is not in equilibrium. It needs to shift. There are too many reactants, these pure acid molecule, and no products. So the change is dictated by Le Chatelier's principle. Which direction is this equilibrium shifting? Is it going to make more products, or is it going to make more reactants? And this is where the change value of either subtracting some amount or adding some amount comes into play. When you look at the balanced chemical equation, all of this is 1-to-1. For every acid molecule, it loses 1 proton at a time. That's why here in this previous case for the phosphoric acid sample, there are 3 separate values, and they're all 1-to-1. Overall, the reaction is that the phosphoric acid is in equilibrium with 3 protons and a phosphate ion, but it happens sequentially and not all of them are off. So you need to know the balanced chemical equation, and typically it's all 1-to-1 for each of these Ka and Kb dissociation constants. So once you have determined which direction the reaction is going to shift, you can then go through and start. You know that the initial concentration of reactant in this case is going to go down by some amount. And the other side is going to increase by that same amount. It's a 1-to-1 relationship. And the concentration of H+ is 1-to-1 with the concentration of this acetate ion. So the concentration of H+ equals the concentration of acetate at equilibrium. So when you have this, it's 0 plus something to give an equilibrium concentration. But the pH value gives you the equilibrium concentration of H+. Remember, when you're measuring something, you're measuring it at equilibrium. So by taking that pH value and converting that to a concentration of H+, you now know the concentration of H+ at equilibrium. And in this example, it's 0.00132 molar. When you start with 0 and you end with this value, that means the X value in this whole ICE table setup is 0.00132. So for the acetate ion, it's 0 plus X, 0.00132. So they're the same. For the acetic acid, the molecule of acetic acid, the equilibrium concentration is now 0.1 minus 0.00132. And this gives a final equilibrium concentration of 0.0987 molar. Now you have the equilibrium concentration of all three components within the equation. You have the equilibrium concentration of the acetic acid, which was calculated, the equilibrium concentration of H+, which was measured by the pH, and the equilibrium concentration of the acetate ion, which was determined by the pH, but really also could be utilized and calculated through the ICE table. Now that all three of these equilibrium values are determined, you can put this into the K equilibrium constant equation, products over reactants. So the products of acetate ion times the H+ ion concentrations divided by the equilibrium concentration of the full acid molecule, in this case, acetic acid. When these three values are plugged in, the Ka, or the equilibrium constant, the acid dissociation constant for acetic acid, is given or is determined to be 1.77 times 10 to the negative fifth. So that's how you would be going through and determining an acid dissociation constant. Just by measuring the pH of an acid, you can figure out, if you know that concentration of acid to start with and you measure the pH, what is the acid dissociation constant of that weak acid. Now, this whole experiment is about buffers and buffering capacity. When you make a buffer, you're taking a weak acid and adding its conjugate base, or adding one of the components to it. And when that happens, things change. So initially, you have, in this example, 100 milliliters of an acetic acid, the same as before. So here are the concentrations of, at equilibrium, of the acetic acid, the H+, and the acetate. So right here. And 3 grams of sodium acetate is added. What is the final pH? And to do this, you're starting out, you're still doing one of the ICE tables. You're still looking at the initial, the change, and the equilibrium. So what I like to refer to it as the pre-initial, kind of what is, before you even perform this, what are the concentrations of everything? This acetic acid is a weak acid. It has a concentration of all 3 components. So these right here, these are the concentrations of the 3 components, the equilibrium acetic acid, the acetate ion, and the H+. Now you're adding 3 grams of sodium acetate. Sodium is a spectator. It's not doing anything. It floats away. But acetate, the acetate ion, is also part of this equilibrium reaction, this dissociation of acetic acid. So there are 3 grams of it, and you're adding this into a total volume of 100 milliliters. So you can take this mass and convert that into moles using the molecular weight of sodium acetate, and then dividing that by the volume. So that gives you a concentration. And all of these ice tables, these equilibrium reactions, are dependent on concentration, not the total amount, but what is the concentration of these different components. And that means there is this much extra acetic acid that was added, 0.366 molar acetic acid, or I'm sorry, acetate ion was added to this system. So now at time equals 0, you add this in and it's time equals 0. There is this concentration of acetic acid. There is this and this together is the concentration of the acetate and the concentration of H+. So now you have the initial stage. This was just kind of how we started off with this ice table up here for determining the acid dissociation. After this, figuring out the concentration of the added component, now we're back to the initial concentrations at time equals 0. In this case, we added one of the products. So the reaction itself is acetic acid breaking apart into acetate ion and H+. So acetate and H+ are the reactants. And we added some of that back into the equilibrium system. We added a product. Based on Le Chatelier's principle, that means the product side has to decrease and the reactant side has to increase. And because the reaction is 1-to-1 throughout the whole equilibrium, what's subtracted on this side is the same as what's added on this side. So we added extra acetate, so that has to go down. The only way it can go down is to react. So it needs to react with some amount of H+, and it's a 1-to-1 relationship. So they both go down by the same amount, and when they react with each other, they form the pure acetic acid molecule. So it goes up by that amount. So now we have the equilibrium is for the acetic acid, the molecular acetic acid is 0.0978. Oops, there's a typo there, I'm sorry. It's 0.0987 molar plus X. For the acetate ion, it's 0.367 molar minus X. And for the H+, the acid, it's 0.00132 molar minus X. So now you would have all three of these components right here, and that will give you the concentrations of the equilibrium components. We've already determined the K value. We've already determined the Ka, or the acid dissociation, for acetic acid. And that was 1.77 times 10 to the negative fifth. So if you have the Ka value, and now you have these equilibrium components of each of the different compounds, you can solve for X. So initially, you'll have to FOIL through that top, because now these are not the same. The concentration of acetate is no longer the same as the concentration of H+. And that's going through, so you'll need to go through and FOIL this out. So front plus outside plus inside plus last. And that gives you this value. And you're then dividing that by 0.0978 plus x, or 987. And this gives an x value here of 0.00131. This can then be plugged back into the change equation. So once you have this x value, you're plugging that back in to finally determine what are the equilibrium concentrations. And the very last step, once you have the equilibrium concentration of H+, you can then convert that into a pH. So this type of an equation, or this type of setup, is a lot of algebra. You're going through, you're looking at the initial, the change, and the equilibrium. You have to foil through this type of setup here, looking at the math, front, outside, inside, last. And then many times you would be using the quadratic formula. And that will give you the x value. And when you use the quadratic formula, you're looking, there are two solutions for it. And you really need to pay attention. You can either do plus or minus the square root. So it gives you two x values. Typically, only one of them would work because you're subtracting a value from this low concentration of H+, and if the x value is larger than that, you can't have a negative concentration. So if the x value is larger than what you're subtracting from, then that's not the correct x value, and it would be the other one. When you're going through and working out on these, working these equations, and it does ask you to show your work, I would just say you just write in the numbers in the quadratic formula, or even just get it to this, set it equal to 0, and then you can use a solver for the quadratic, and just give x equals this. The quadratic formula is a decent amount of algebra, and you don't necessarily need to show that part of the work. Just setting this up and getting it to this format would be good enough.
As mentioned, this experiment is looking at determining the Ka values and the Kb values. These are the dissociation of acid and base. So as an acid molecule breaks apart, or a base molecule breaks apart, what is the equilibrium constant for that dissociation, for that reaction? You've already looked at other types of equilibrium. You've looked at generally just Keq, or the equilibrium constant of any equation. You've looked at Ksp, or the solubility product, which is the equilibrium constant for the dissolving of a solid in solution. And you've looked at the formation constants, or the equilibrium constant for the formation of a complex ion, such as cobalt tetrachloride. And this experiment is looking at the formation of, or not formation, but the dissolving, the equilibrium of the dissolving of weak acids and weak bases. And that subscript of A or B simply denotes that it's the K value of an acid, or the equilibrium value of an acid dissociating, or of a base dissociating. And going through and calculating these equilibrium constants, when you do that, you can see a more detailed approach of what that chemistry is, what type of chemistry is happening for these different acids and bases, and which ones have a relatively stronger character.
Now, I mentioned a bit ago about the acid and its conjugate base. And conjugate acids and bases are pairs of an acid and a base. And the terms conjugate acid and base does not mean that they are acidic or basic in absolute terms, but they're acidic and basic relative to each other. So in the case of the phosphoric acid that was brought up earlier, you have the acid. The acid is something that loses a proton, and its conjugate base is what's left over. So there's the H plus that goes away, and the other component is the conjugate base. The H plus also has a conjugate base of water. But in this case, looking purely at the phosphoric acid loses a proton, and its relative base, or its conjugate base, is H2PO4-. This compound, this ion, H2PO4-, is still very acidic, but it's a base relative to the phosphoric acid itself. And this conjugate base still has 2 protons. So that means it can be an acid and a conjugate acid relative to this other, its conjugate base of HPO4-2-, which can then itself be a conjugate acid to the conjugate base of PO4-3-. So a conjugate acid-base pair is differs only by a single proton. A conjugate acid will lose 1 proton, and then that will be the conjugate base. The conjugate base is capable of adding 1 proton to become the conjugate acid. And all of these are in equilibrium, so they can move back and forth. And there are a lot of different conjugate acid-base pairings that play a very critical role in the preparation of buffers. Buffers themselves are a mixture of conjugate acid-base pairs. So by adding in this previous example here, this middle reaction is a very common buffer solution, a phosphate buffer solution, where you have diprotic phosphate, or many times this would be referred to as monobasic, so it has reacted once, and dibasic, meaning it's reacted twice in total. And mixing these together in specific ratios, these are able to buffer against pH changes. Because of the chemistry and because of Le Chatelier's principle, keep trying to maintain that equilibrium. If you add some outside acid, the equilibrium shifts and it just uses up that acid to make more of this, the H2PO4. If you add base, well, the H2PO4 can react with some of that base and make HPO4-2-. By adding additional acid or base, the reaction of this equilibrium and Le Chatelier's principle can utilize that additional acid base in order to maintain a relatively constant pH. And a buffer capacity refers to the ability to maintain that pH or resist a change in pH. These buffers are incredibly important in many types of biochemical or biochemistry settings where different enzymes, different proteins and things only work at a very, very specific pH. So it needs to be buffered or be prepared in a solution that resists any large fluctuations in order to maintain that constant pH. When you have something that's a very good buffer, if you add a little acid or a little base, the overall pH changes very, very little. In the case of something like water, it is not a buffer at all. If you were to measure the pH of water, like you will do in the virtual lab, and then add just even the tiniest amount of acid or tiniest amount of base, the pH changes by a large amount. It has no buffering capacity. But a buffer will be able to resist that pH change and hold its pH relatively constant. Now, it will change ever so slightly because you're adding an acid or base, but when you're looking at buffering capacity, you're looking at these in relative terms. And in the lab, you're going to be preparing two buffers and looking at their buffer capacity relative to each other. Which one changes pH the least when you add acid? Which one changes the pH the least when you add base? Now, buffers themselves, as I mentioned, you can prepare buffers in a number of different ways. It's a mixture of a conjugate acid-base pair. And if you mix these two components in different ratios, it's still going to be a buffer, but now it's going to be a different pH. It's going to start at a different initial pH and will buffer at that particular pH. So you can have an acetate buffer at pH 6 or at pH 5 or at pH 7, and it usually hovers around the pKa, which is the negative log of the dissociation constant, or the Ka value. And around there is where it has the best buffering capacity. But things like acetate buffers, phosphate buffer, ammonia buffer, these are not fixed at one pH, but a variation around a number of pHs, and that's depending on the ratio of its conjugate acid and conjugate base. So if you have a buffer and add one of these components, it's still going to be a buffer. It's just going to be starting at a different pH.
The pH, which the buffer hovers around, is related to the pKa of the equilibrium reaction. The pKa value is the negative log of the acid dissociation constant, or the Ka, or in the case of ammonia, Kb. You can see with each of these different solutions that when universal indicator is added, the different buffers all create a different pH. With the acetate buffer indicating an acidic pH, the phosphate buffer indicating a neutral pH, and the ammonia buffer indicating a basic pH. These can be measured even further by looking at the specific pH values using a pH meter. This particular buffer solution of acetate buffer is at a pH of 4.56. The phosphate buffer solution is prepared at an approximate pH, or at a more specific pH, of 6.93. And the ammonia buffer is prepared at a pH of 9 point at 9.83. All of these buffer solutions are prepared using conjugate acid-base pairs, and the different pairings based on the equilibrium constants generate buffers that are hovering around a specific pH. While the general pH of a buffer is determined by the acid dissociation constant and the equilibrium constant, the specific pH of each solution is determined by the concentrations of the conjugate acid and base pair. All 5 of these solutions are solutions of acetate buffer, ranging from pH 6 to a pH of 4. If we look at these buffers using universal indicator, we can see the gradual pH range and how it changes as a function of the concentration between the conjugate acid and base pairing. At a pH of 6, it's more of a golden color. At a pH of 5.5, it's starting to become more orange. At a pH of 5, it's beginning to be even more orange and almost a red color. At a pH of 4.5, it's moving even farther into the red range. And at a pH of 4 is a darker red solution. All 5 of these solutions are the same buffer. They are all acetate buffer solutions. But by varying the concentration of the acetic acid and the acetate base, you can vary the specific pH that the buffer protects against. In the case of the pH 5.0 acetate buffer, the pH is buffered and will maintain a pH of 5.0, while the 5.5 buffer will maintain a pH of 5.5, given any sort of outside acid or base interference. These buffers play a critical role in a lot of biological processes, as many enzymes and proteins will only work at very specific pHs.
One final topic to cover in terms of acid-base chemistry would be that of titrations, or a titration curve. Now, you've done titrations in the past, and you have used them to determine stoichiometric ratios and determine endpoints. A titration is something where you're measuring a specific property stepwise as you're adding something else. This can be done in terms of pH, absorbance using a spectrophotometer, enthalpy using a calorimeter, or a number of other different properties which you can measure that change as a function of something else. In a pH or in an acid-base setting, this measured property would be the pH of the solution. And as you slowly and stepwise or continuously add a component that changes the measured property, you can develop what's seen as a titration curve. And these titration curves can give you some very important stoichiometric information. First off, you can see that in this titration curve, it is 0.1 molar acetic acid, titrated with 1 molar sodium hydroxide. So there is a solution of acetic acid, and sodium hydroxide is slowly being added to that solution. And initially it has a very low pH because it's an acid. And as you're adding more and more of the sodium hydroxide, you can see that the pH is changing slightly all the way up to a certain point where it jumps and then continues on in a very slight manner. And it's this jump, this transition in a titration curve that can give you a lot of information. And the specific point on this titration curve is the very center of this jump, or the inflection point, where the rate of change or the derivative of this changes directions. And this is what's termed as the equivalence point. This is the point on the graph where the moles of titrant, or what you're adding, is equal to the moles of what was in the initial flask. So in the case of this acetic acid and sodium hydroxide curve, at this point, this equivalence point, the moles of acetic acid is equal to the moles of sodium hydroxide. They are equivalent to each other. And from that point, you can figure out stoichiometrically, if you had an unknown, you can use this to determine what the concentration of the unknown is. And you can also see that when they are equal, all the acetic acid has been neutralized. The pH reading of this is not exactly 7. The pH reading is about 8.6 based on this curve. That's because you're mixing a weak acid with a strong base, so the resulting mixture at the end, when everything is neutralized, would be a slightly basic solution. Now, many times in a titration, you might be using an indicator. And an indicator is a chemical that can be added to the solution. It does not really play a role in the reaction itself, but it is a visual indication of when the reaction is complete. These are many times color change indicators, and they will change color based on the pH. And choosing an indicator to figure out where these two meet, it's based on that pH. So an indicator that changes color at around 4 would not be very good in determining where these two things are equal to each other, where that equivalence point is. But an indicator that changes color around between 8 and 9 would be a very good choice for this, because it would change color and show you where the two are equal to each other in terms of the pH. So when it gets to a pH of about 8.6, the indicator would change color, and you can see that in the curve, because the equivalence point, or at the equivalence point, the moles of acid is equal to the moles of base. This experiment that's done in lab is kind of an involved experiment. You're going to be measuring the pH of a number of different solutions, preparing different buffer solutions and testing them, and performing a titration, all of which revolves around pH measurements. In the first part of the experiment, you're going through and measuring these 5 different solutions. You're measuring the pH of these 5 solutions, and you're going to measure that by 3 different methods: by use of pH paper, by use of a pH indicator, and by use of a pH meter. So in each of these, you can tell by the pH whether it's an acid or base. And from the pH measurement, you can obtain the pOH measurement, and you can obtain concentration of H plus and concentration of OH minus to determine whether or not these are strong or weak acids and bases, which ones ionize completely and which ones ionize only partially. And when you go through and look at that, you should be able to tell the difference between a strong solution, a strong acid or a strong base, and a weak acid or a weak base, and what that has to do with the percent ionization.
Before beginning to use the pH meter, it must first be calibrated each time it's powered on. The pH electrode is stored in a solution so that it does not dry out. You will first need to remove the electrode itself from its housing, and then, using your wash bottle, you will rinse off the storage solution. This is done just with plain tap water. The pH electrodes themselves should not dry out and should not be left outside of a solution for extended periods of time. You'll notice that on the pH meter itself, there is a display icon that says MEAS for measure. This is the type of mode the pH meter is in. To calibrate the pH meter, you would select calibration or measurement and change it to calibration mode. This is indicated on the display as CAL. To begin the calibration, you'll first select the pH 7 buffer solution and place the rinsed electrode directly inside the solution. As the solution and the pH electrode equilibrate with one another, you'll notice the measured pH changing. When the indicator light displays ready, you can then select Enter, and the value instantly changes to the appropriate pH. You will then repeat this with both of the other buffer solutions, the pH 4 buffer and the pH 10 buffer, being sure to rinse the electrode in between each measurement. You can place it then into the pH 4 buffer solution, and you'll see that it self-selects for the pH 4 buffer. Once ready is displayed, you can then press Enter and allow it to adjust for the pH 4 buffer. The last buffer itself is pH 10, where you would first rinse off the electrode and then place it into the pH 10 buffer solution. As the solution itself equilibrates with the pH meter and the electrode, ready will be displayed on the indicator. And when you press Enter for this last time, the pH meter is now calibrated and by default switches back into measurement mode. At this point, The pH electrode and pH meter are now fully calibrated and ready to measure multiple different solutions to determine their pH. In the first part of the experiment, you will be measuring the pH of a number of different solutions using multiple different methods. You will be measuring acids and bases using pH paper, a pH indicator solution, and a pH meter. When using the pH paper, this is very similar to a backyard pool pH strip. You can take the individual bottle, open it up, and simply dunk the pH strip inside, making sure all of the pads are wetted with the solution. You can then compare the results to the indicators on the box of pH paper. This will give you a whole number pH range between 0 and 14. The second method of measuring the pH is done through a pH indicator solution. The indicator changes the color of the solution as a whole, and so should be done in a separate test tube. You can take a small amount of your solution and place it in a test tube, and then add a few drops, 1 or 2 drops, of universal indicator. What this does is changes the color of the entire solution. This color can then be compared to the chart that's associated with universal indicator to give a
report. The calculations are really just revolving around the pH. So in kind of the first part, you're recording the pH, and from that pH value, you can get the pOH value. From the pH value, you can determine the concentration of H+, and from the pOH value, you can determine the concentration of OH-. You can also determine the equilibrium constants for the weak acids and weak base. So for the acetic acid and the ammonia. So from the pH, you can determine the concentration of H+, and from the balanced chemical reaction, if you know the concentration of H+, you know the concentration or the equilibrium concentration of the acetate, and can determine the equilibrium concentration of the pure acetic acid, since the initial concentration of acetic acid is known, and then solve for what is the Ka, what is the acid dissociation constant for acetic acid. From the pH value, you can also calculate a pOH, and this is where you'll be solving for the Kb of the ammonia solution. So for the ammonia solution, you're looking at the pOH and then determining the concentration of hydroxide itself, the concentration of base, and then using the balanced chemical equation, the concentration of hydroxide will equal the concentration of ammonium, and the equilibrium concentration of ammonia will equal that initial concentration of ammonia minus the concentration of base. So from those values, you can then determine the Kb for the ammonia solution.
The second part of the experiment deals with preparing and testing different buffer solutions. In the lab, you will be preparing 3 buffer solutions, and the specific amounts of the two conjugate acid and base pairings are found in the procedure. You will use a pipette to deliver precisely the exact amount needed of each of the different solutions. When using a pipette, you can draw up the solution using a pipette pump to the 0 mark and deliver the appropriate amount. In this example of phosphate buffer, I need to deliver 6.17 milliliters of sodium phosphate dibasic. When it reaches the 6, that is exactly 6 milliliters that has been delivered to the volumetric flask. And you will then deliver 6.17 milliliters of sodium phosphate dibasic. Additionally, you will add 3.85 milliliters of sodium phosphate monobasic. With the two solutions added to the volumetric flask, you can then fill it to the mark with regular tap water. You can fill the bulb of the volumetric flask by pouring the solution in, or pouring the water in, and when you reach the neck, you should go more slowly using a pipette to be sure that you do not add water to the volumetric flask, and you're able to make it exactly to the mark, indicating that the solution prepared is exactly 100.00 milliliters. You can then stopper the flask, invert it a couple of times in order to ensure that the solution is properly mixed. And now you have a buffer solution that's prepared. You will prepare a phosphate buffer, an acetate buffer, and an ammonia buffer, and then using these buffers, test their different properties. When testing your buffers, you will test all three of your buffer solutions as well as tap water to see their buffering capacity against both acid and base. Initially, you will measure out 50 milliliters of tap water and add this to two separate beakers, 50 milliliters each. You can then record the pH of the tap water itself. You only need to record the pH of one of these as they are both the same. When the pH of the solution is recorded, remember you're recording the pH of water and all three of your buffer solutions. You will then add to one of these beakers 1 milliliter of 1 molar sodium hydroxide. And you'll record what the pH is for that solution. You'll then rinse off your electrode and place it into the other beaker, to which you will add 1 milliliter of 1 molar hydrochloric acid. So for each of your 3 buffer solutions, you will be measuring the pH of the buffer itself as well as tap water, and then separating them out into 2 separate portions, and to each portion adding 1 milliliter of hydrochloric acid and seeing the resulting pH, and 1 milliliter of sodium hydroxide to the other beaker and seeing the resulting pH. You should be able to see, based on the change in pH, which of your 3 buffers is best for maintaining a constant pH under acidic conditions and which one is best under basic conditions. In addition to these tests, you will perform one additional measurement using your acetate buffer. You will measure out 20 milliliters of your acetate buffer and add that to a small beaker. You'll then record the pH of the acetate buffer using the pH meter. Next, you will weigh out approximately 1 gram of solid sodium acetate trihydrate and add this directly to the acetate buffer. Using your stirring rod, you can then stir the solution and allow the sodium acetate to dissolve. Once the sodium acetate is dissolved, you can then measure the pH of the resulting solution and see what a change happens when additional acetate ions are added to a buffer, and see what the resulting pH is. Because you used 20 milliliters of your acetate buffer already, when performing the additional measurements with hydrochloric acid and sodium hydroxide, you'll only need to measure out 40 milliliters in each separate beaker. This ensures that you're able to utilize all 100 milliliters of your prepared acetate buffer.
In the second part of the experiment, you're preparing and testing 3 different buffer solutions. You're preparing a total volume in each case of 100 milliliters using your 100 milliliter volumetric flask, and the total volume of stock solution, that's the conjugate acid and the conjugate base in each of these 3 buffer solutions, is a total volume of 10 milliliters. So the resulting concentration of your buffer will be a 0.1 molar buffer solution. In the case of the acetate buffer, you're taking 8.20 milliliters of a 1 molar acetic acid solution, placing that into your volumetric flask using a pipette, and then adding in 1.80 milliliters of 1 molar sodium acetate solution, and bringing that up to the mark with water. You can use regular tap water. So when you do this, you'll can then measure the pH of all 3 of your buffer solutions, as well as test them to see how they perform or how the pH changes in acidic conditions or in basic conditions. And to do that, you're going to be splitting your buffer solution in half. The acetate buffer does have one additional step. So throughout this, you're going to be measuring the pH of water, your acetate buffer, your ammonia buffer, and your phosphate buffer. And then you're going to prepare a few small beakers, 50 milliliters in 2 of the beakers of water. To one of them, you'll add acid. To one of them, you'll add base. And you're just going to see how that changes the pH, how far apart that pH changes by the addition of acid and by the addition of base. And you're going to repeat that experiment or repeat that procedure with each of your 3 buffers. You're going to take some of your acetate buffer and add acid and see how much the pH of the solution changes. You'll also do the same thing with the sodium hydroxide. And see how far the pH changes. You'll repeat that also with the ammonia and the phosphate buffers. In the end, you're looking to see which one of these buffers is best for maintaining its pH under acidic conditions and which one maintains its pH best under basic conditions. The acetate buffer also has one additional test, and that's where you will take 20 milliliters of your acetate buffer and weigh out approximately 1 gram of solid sodium acetate trihydrate and dissolve that into your 20 milliliters of acetate buffer. And when you do that, you will notice the pH changes. You're just going to be measuring the pH before and the pH after the addition of the 1 gram of sodium acetate trihydrate. And you can use this to predict what the pH is going to be. So when in this particular instance, in this problem, you have a buffer and you're adding additional conjugate base. This is an acetate buffer of acetic acid, acetate, and H+. Those are the 3 components in the buffer. And in this situation, you're adding additional acetate. So the starting concentrations, these are the concentrations of your buffer itself before adding anything. So you prepared this by taking 8.2 milliliters of a 1 molar solution and placing that in 100 milliliters total volume. You diluted the acetic acid. You also diluted the 1.8 milliliters of 1 molar sodium acetate solution. So you have these starting values. You can use those just based off of the dilution. And you have the pH measurement. You have what the concentration of H+ is based on the pH of your buffer itself. So that is the setup of this question in the lab report, where you have the concentrations initially, and then you add additional sodium acetate. So you're adding an additional concentration here, and that changes things in that equilibrated acetate buffer system. So now you have new initial concentrations. And using Le Chatelier's principle and using this ice table, you're going to determine what is the equilibrium concentration of these 3 components and what the final pH would be of that combination of acetate buffer with additional acetate ion.
Many times, when filling the burette, it may be easier to fill the burette above the 0 mark. And then drain the volume from the base of the burette. until it reaches exactly the 0 mark. By doing it this way, you will then ensure that the tip of the burette is also filled with the sodium hydroxide. When the burette is filled, you can then start to perform the titration. You may leave the electrode inside your phosphoric acid. You will add exactly 1 milliliter of sodium hydroxide to your phosphoric acid from the burette, and then record the resulting pH measurement. You will record the pH after each 1 milliliter addition of sodium hydroxide. In total, you will be adding 25 milliliters of sodium hydroxide to your phosphoric acid, recording the pH with each addition. From this data, you can generate a titration curve, plotting the pH of the solution on the y-axis and the total moles of sodium hydroxide added on the x-axis. In the third part of the experiment, you will perform a titration of phosphoric acid and sodium hydroxide. You will first measure out 50 milliliters of 0.1 molar phosphoric acid. This will be placed in your Erlenmeyer flask, and you can then record the pH of the solution using your pH meter. While this is equilibrating, you can then fill a burette with 0.5 molar sodium hydroxide.
Phosphoric acid itself is a triprotic acid. That means that for every 1 molecule of phosphoric acid, there are 3 H+ ions that can break off and react with hydroxide. So for every 1 whole molecule of phosphoric acid, this can react with 3 sodium hydroxides to produce 3 water molecules and 1 sodium phosphate. However, these 3 protons do not break off all at once. Phosphoric acid is a weak acid. That means it does not ionize 100%. And it goes through a stepwise reduction of these H+ ions. So where you first have phosphoric acid, this is in equilibrium with the ion dihydrogen phosphate. This itself is in equilibrium with monohydrogen phosphate, which is again in equilibrium with the phosphate ion. Each one of these is its own acid-base reaction, and each one has its own individual Ka value, because these are all occurring in equilibrium. In the titration, you're going through and looking and determining the equivalence points of these first 2 reactions. The third reaction can occur, but not under these specific conditions that you're doing in the simulation. So since they occur in a stepwise order, and as you react more and more, it's becoming more and more basic. The pH is increasing with each additional step. So you should be able to see this third one if you were to keep going using very, very strong and highly concentrated sodium hydroxide. If you want, you could try to test that out. But under these conditions and the conditions of the simulation, you won't actually see this third step. But when you perform the titration and you're stepwise adding sodium hydroxide, you should be able to see these first two steps of the reaction and determine the equivalence point for each one of these two individually.
In the end, this experiment predominantly looks at measuring the pH of a number of different solutions and converting that into the concentration of acid, that H+ concentration, as well as the concentration of base, the OH- concentration. You're also looking at, from the pH measurement itself, looking at developing the Ka and Kb for varying solutions of weak acids and weak bases. What is the equilibrium acid dissociation constant, or the base dissociation constant? And finally, you're looking at preparing buffers, which are resistant towards a pH change. You're figuring out which ones are better for acids, which ones are better for bases, and overall getting a good sense of what buffers are actually comprised of and what they actually do.